Hello into another lecture of construction equipment, and today we're going to be talking about loading and hauling. So primarily in this lecture we're going to learn about how to calculate the cycle time and what are the elements affecting the cycle time. Primarily, what kind of resistance is the equipment going to be subject to that can affect its performance. It can affect the duration of the cycle time and the number of cycles per hour. So the equipment productivity is affected by several things. Speed affects the cycle time, speed of each cycle. The cycle time affects the production, because again the production is determined by the number of cycles per hour times the production per cycle, and the number of cycles per hour is determined by the length of the cycle time. And production determines cost. So primarily we can say that the speed of the performing the operation for each cycle affects the project cost for that piece of equipment. Each piece of equipment requires a certain amount of power to overcome the resistance that it's going to be facing. So the required power is the power needed to overcome resisting forces and cause machine motion. So for example, imagine that you are driving in a muddy condition. There's going to be a certain resistance to the motion of the tires. So the equipment has to be able to overcome that resistance in order to move forward. The magnitude of the resisting forces determines the power required, the minimum amount of power required to overcome this resistance and to be able to move the vehicle or the equipment forward. The equipment cycle time, the cycle time for a piece of equipment is the time it takes to perform one cycle of its planned job. We mentioned in the last class that one cycle is basically going to be, for example, for a loader, is to position itself instead of the area to be excavated or in front of the soil to be removed, and then to load that soil in the bucket, to turn around and to move, to dump that soil, and then to come back, position itself and get ready for a new cycle. All of this forms one cycle. So loading, hauling, excavating, lifting, etc. All of these are parts of the cycle time for the equipment. And each cycle consists of two components. One of them is called fixed cycle part or fixed cycle time or fixed component of the cycle time, and the other one is the variable component of the cycle time. The fixed time is the part of the cycle other than the travel time. Includes spotting, loading, maneuvering, and dumping. So mostly the fixed time is done while the equipment is in its place. It's not moving. Loading takes place while the equipment is standing in place. Dumping is the same thing. Whereas traveling back and forth, this is the hauling part of the cycle time, which is going to be part of the variable time. So the variable time represents the travel time from origin to destination and back, and it depends on equipment characteristics like the weight and the power, the engine power of that equipment, the road conditions, whether it's flat or bumpy, whether it's uphill or downhill, what kind of soil is it rolling on, grade and altitude, again grade, which is the slope of the road, again downhill or uphill, altitude, as we have discussed in class, the higher from the sea level you're working, the thinner the air is going to be, which might affect the efficiency of the engine, and the distance traveled. Of course, the farther the distance, the longer it's going to take to get to and from there, the longer the variable part of the cycle time. The loading time is a function of the capacity and cycle time of the loading equipment, the capacity of the truck or hauler, and the skill of the loading operator. If you remember what we discussed before about excellent job conditions, above average, average, below average, etc., it had something to do with the angle of swing, for example, of the equipment. The larger that angle of swing, the longer it's going to take, which means it's going to take, the cycle time is going to be longer. Whether it's dumping on the ground or it's dumping in a truck, whether the truck is a large truck or a small truck, how skilled the truck driver is, how big is the bucket for the loading equipment, and how big is the bed of the truck where you're going to be dumping the soil. All of these are elements that affect the loading time. The dumping time is affected by the type and condition of material, how easily is it going to flow from the bed or from the bucket of that equipment, whether that material is going to be wet or dry, the method of dumping or spreading, whether it's going to be end dump or bottom dump, or whether you're going to be dumping into a pile or you're going to be spreading it around, and the type and maneuverability of the truck or the piece of equipment, basically. So the haul and return time are a function of the haul road profile, including the grade resistance, rolling resistance, and distance to be traveled. We're going to talk about each one of these in more detail in a second. The altitude of the project site, and the performance characteristics of the hauling equipment, which is a characteristic of the vehicle itself or the equipment itself. Number of loader cycles to load a truck. So if you have, let's say, a loader with a bucket size of 2 cubic yards, and you have a truck with a capacity of 15 cubic yards, how many cycles is it going to be needed to load the truck? The volume capacity of the truck divided by the volume capacity of the loader. So in this case, it's going to be 15 divided by 2, which is 7.5, which means it's going to take 8 cycles. Now, the number of loader cycles required times the loader cycle time is going to determine the loading cycle. So to fully load that truck, you're going to need 8 cycles of that loader. If each cycle takes, let's say, 35 seconds, then it's going to be 8 times 35 seconds. That's going to be the duration of loading that truck. And here, for example, are some examples in this table about the job conditions, whether it's favorable, average, or unfavorable, for the turn and dump time and for the spotting time, which are basically all of these are part of the fixed time of the equipment. This is not the variable time, this is the fixed part. So in under favorable conditions, in end dump it's going to take about 1 minute. The spotting time is going to be about 15 seconds. For the bottom dump, it's going to be less than that, only 0.4 minutes, and the spotting time is going to be pretty much the same. So under favorable conditions, the fixed time for that piece of equipment is going to be, for an end dump, is going to be 1 minute and 15 seconds. Under unfavorable conditions, as you can see, that number is going to be much larger, 1.5 to 2 minutes and 0.8 minutes, so almost twice as much as the favorable conditions. Now talking about the resistance, what kind of resistance is the equipment going to be facing while it's trying to move and to perform its function? Rolling resistance is the first type, and it's a measure of the force. The force is going to be expressed in pounds per ton that must be overcome to rotate a wheel over the surface on which it makes contact. So this is friction is going to be part of that equation. One of the types of resistance an equipment faces while moving. So we have 2 types of resistance the equipment has to overcome. One of them is going to be rolling resistance, and the other one is going to be the grade resistance. It can be expressed either in as a pounds per ton or of equipment weight, or just in pounds. So you can say either the rolling resistance is going to be 20 pounds per ton of the equipment weight. So if the equipment weight is 20 tons, then the total resistance, rolling resistance, is going to be 20 pounds per ton times 20, which is the weight of the equipment. That's 400 pounds. Or you can just express it as number of pounds, again, as we did by multiplying that factor in pounds per ton by the total weight of the equipment. Now that weight of the equipment is going to change because whether the equipment is empty or is loaded. So when it's loading and going to dump, it's going to be moving forward full, so it's going to be heavier, therefore the resistance is going to be much more. When it's coming back, it's going to be empty, therefore the resistance is going to be less than the previous case. It is caused by internal friction and tire flexing. Tire flexing is very important. So as you know, to improve your fuel efficiency for your vehicle, for your car, properly inflated tires are going to yield better fuel consumption. Same thing here. It's going to increase, that rolling resistance is going to increase by about 30 pounds per ton for each inch of tire penetration. Tire penetration into that soil, if the tire is penetrating 2 inches, then that's going to add 60 pounds per ton of rolling resistance. Properly inflated tires reduce rolling resistance. What if the equipment is rolling over asphalt or concrete? Now in this case you're not going to have any tire penetration, so you're not going to have much additional rolling resistance due to tire flexing. If the tire penetration is known, then the rolling resistance is equal to, which is RR, that's the rolling resistance. It's 40 pounds per ton of the equipment weight plus 30 pounds per ton per inch times inches of tire penetration. So again, if you're rolling on concrete or asphalt where you're not going to have any tire penetration, that second part of the equation is going to be equal to 0. You're only going to have the 40 pounds per ton. The rolling resistance force, so this is the rolling resistance, but the rolling resistance force for the whole equipment is going to be the rolling resistance in pounds per ton, which we calculated from here, the RR, times the total weight of the equipment in tons. That's going to be a force represented by or expressed in pounds. If tire penetration is not known, then the rolling resistance can be estimated from tables. So you don't know exactly, you can't measure the tire penetration, but you know what type of soil that equipment is going to be working on. We can use that table. So for concrete or asphalt, the rolling resistance factor in pounds per ton is going to be 40 pounds per ton, which is basically this one, with the second component of the equation being equal to 0. For concrete is going to be 40, for asphalt is going to be 30. Firm, smooth, flexing slightly under load. So we're not talking about the paved road, we're going to talk about a compacted dirt road, for example. That's going to be up to 64 pounds per ton. Rutted dirt roadway, 1 to 2 inches of penetration is going to be 100, which is basically the 40 plus 30 pounds per ton per inch times 2 inches, which is going to be 60. So 40 plus 60, that's 100 pounds per ton. Soft rutted dirt, 3 to 4 inch penetration, about 150. Loose sand or gravel is going to be up to 200 pounds per ton. Soft, muddy, deeply rutted road conditions is going to be anywhere between 300 and 400 pounds per ton. You can see the big difference between a paved road, concrete or asphalt, 40, and soft, muddy, deeply rutted, 300 to 400, which is 10 times the rolling resistance. Therefore, these are things that you can control as a project manager. For example, you can build a temporary access road, or you can have compacted soil or crushed stone or gravel or something like that to improve the working conditions of the equipment, therefore reducing the rolling resistance, which means you're going to get better cycle time, which means higher productivity and lower cost. The second type of resistance is the grade resistance, which is the component of a vehicle's weight which acts parallel to an inclined surface. It can be positive when moving uphill. Contrary to our intuition, you might think that positive is something good that helps and negative is something that impedes. Here we're going to use the opposite sign convention. It's positive when moving uphill, so you're going to add that resistance when moving uphill. It's going to be working against the equipment, which is adverse conditions, and negative when moving downhill, which is a favorable condition, also called grade assistance, not resistance in this case, grade assistance, which means it can help reducing the rolling resistance. And it can be calculated exactly the same way as we did with the rolling resistance. The grade resistance can be expressed in pounds per ton, which is equal to 20 pounds per ton for each 1% slope times the percent slope. So if the grade is 5%, moving uphill by 5% is going to be 20 pounds per ton for each 1%, which is 20 pounds per ton times 5, which means we're going to have a grade resistance of 100 pounds per ton. If the weight of the equipment is 20 tons, again, 100 pounds per ton, which is 20 times 5 times 20, that's going to give you the total resistance, the total grade resistance force. So the grade resistance force is equal to grade resistance, the factor that we calculated from here, times the total weight of the equipment in tons. Again, in this case, the issue of whether the equipment is loaded or unloaded is going to make a big difference. Can we express both resistances into one? So can we express both rolling resistance and grade resistance as a common number? Effective grade is the grade resistance equivalent to the total resistance encountered by the vehicle. So you can say, for example, that a vehicle that's moving on a flat surface, but the road is rutted and is going to exert a lot of rolling resistance, that is as if the equipment is moving uphill on a certain slope. It's also called equivalent grade or percent total resistance, and can be calculated as the effective grade percentage is equal to the actual grade if it's moving uphill at 5%, so that's going to be 5, plus rolling resistance divided by 20. So if the rolling resistance, for example, is let's say 100 pounds per ton, then we divide that by 20. That's going to be 100 pounds per ton is going to be equivalent to moving uphill at a 5% slope, which is the 100 divided by 20. So in this case, if you already have a 5% slope plus rolling resistance of 100 pounds per ton, that's equivalent to moving up to a 10% slope uphill. Of course, that also is affected by the type of soil that you're rolling on. Imagine if you're rolling on ice, you're not going to have any traction with that ice, so the tires or the wheels can turn without the equipment moving forward. So we're going to deal with something called a coefficient of traction. The power available to move the vehicle and its load can be expressed as either, if that equipment is running on wheels, it's going to be called the rim pull. Rim pull, which is the pull available at the rim of the driving wheels under rated conditions. The driving wheels, some equipment are four-wheel drive, some of them are two-wheel drive, some of them have more than two moving axles. So an equipment might have 3 axles, for example, 2 of them are moving axles. So in this case, we're going to calculate that pull available at the rim of the driving wheels, which is the moving axles. If that equipment runs on tracks, then it's going to be called drawbar. So we're talking about rim pull in case of wheels, drawbar in case of tracks, which is the power available at the hitch of the crawler tractor operating under standard conditions. How much pull can it exert? How much weight can it pull? The traction depends on the coefficient of traction and the weight on the drivers. So the maximum usable pull, you might have a lot of power for the equipment, you might have a lot of rim pull, a lot of drawbar, but especially a lot of rim pull in this case, but you're working on a very slippery soil, so the wheels turn in place, therefore it's not all translated into motion. So here we have something called a coefficient of traction. For concrete that's dry, it's going to be 0.9, which is 90% of the power is going to be translated into motion, whereas for tracks it's only 45%. Concrete that's wet, 80% and 45% respectively. And you keep going down until we reach, for example, ice. It's only 10%. 90% of the power of the equipment is wasted. And in case of tracks, it's going to be 85% of that power that's going to be wasted. So the maximum usable pull is the coefficient of traction, which we can obtain from such a table depending on the soil conditions, times the weight on drivers. Not the weight of the whole equipment, but the weight on the moving axles. That's going to be what affects the motion of the equipment. That's why, if you remember in the last lecture when we were talking about that coefficient of traction, in case you are driving uphill on an icy road or where you have snow, it might, especially in a rear wheel drive car, putting a heavier weight on the rear axle, like having sandbags in your trunk, for example, in the trunk of your car, might help overcoming that kind of resistance. The equipment available power is the engine horsepower and operating gear. The engine horsepower and operating gear are the primary factors in determining the power available at the drive wheels or the drawbar of a machine. Drawbar in case of tracks, rim pull in case of wheels. Horsepower involves the rate of doing work, and 1 horsepower is equivalent to 33,000 foot-pound per minute. Therefore, the traveling speed of the machine should be considered when calculating the amount of pull, since we're talking about per minute, so we're talking about speed, which is going to be a factor. Performance charts are provided by equipment manufacturers to enable the calculation of the estimated machine speed. So with each piece of equipment, you're going to have a manual that has some performance charts that tells you under first gear what's the maximum attainable speed, or second gear, third gear, fourth gear, under different loading conditions, whether the equipment is fully loaded or it's empty, its gross weight or net weight, and so on and so forth. The charts relate rim pull or drawbar pull to gross vehicle weight, speed, and total resistance as a percent, which is the effective grade. Here's an example of a performance curve. It shows both in kilograms or in pounds, so metric and imperial. And that's the drawbar pull. And this is the speed that the equipment can reach. And it tells you here under such and such speed, under such and such gear. So under the first gear, your maximum speed is going to be about 2.5 miles per hour. Under the second gear, your maximum speed is going to be about 4.25 miles per hour. And the overall maximum speed of that equipment is going to be less than 7 miles per hour. So knowing the drawbar pull, here for example, 25,000 pounds, we go horizontally, is going to intersect with two different gears. So under the first gear, with that 25,000 pounds of available drawbar, available pull, we're going to have about 1.4 miles per hour, and under the second gear, we're going to have only about 1 mile per hour. Here's another example of these sets of performance curves. It shows at the top the gross weight of the vehicle, and it shows when it's empty, that's the weight, and this is when it's loaded. So we can do the same thing. The gross weight, the rim pull, the total resistance, which is grade plus rolling resistance. We converted the rolling resistance into grade by dividing it by 20. And each, that's going to be represented as percentage points. So here, for example, if that vehicle's weight is about 100,000 pounds, and it's running over a surface with an effective grade of 6%, then in the fourth gear, it's going to give us a speed of about 14 miles per hour, and that's got the available rim pull is going to be, or the required power to generate is going to be around 6,000 pounds. Here we have something called a retarder curve. If that equipment is moving downhill, again the same piece of equipment, here's the weight, and it's moving, the effective grade is a favorable grade, moving downhill 20%. In the second gear, it's going to give us a speed of about maybe 7 miles per hour. And if it's empty, this is when it's loaded. If it's empty, same equipment and moving again on the same slope, it's going to give us, also in the second gear, it's going to give us about the same speed, which is about 7 miles per hour. Now, what if that equipment, imagine if the road is divided into different segments. Part of it is uphill, part of it is flat, and part of it is downhill. Depending on the length of the segment, if the equipment is going to move in very short segments, it's not going to gain enough speed to move faster. So the longer the segment, the better the factor that we're going to use here. And we're going to see how to use that factor in a minute. If the length of the segment is only 100 feet, it has to start and stop in 100 feet. It hasn't gained enough speed. but if it's moving 5,000 feet, it's going to give gain 96% of its maximum speed. Here it's going to have only about 45% of its maximum speed. And then we're going to have to compare whether it's coming from a stop and going uphill, or coming from a stop moving downhill. Is it increasing or decreasing speed? We're going to see all of these in a problem in a moment. If the truck stops at both ends of a segment, divide the segment length into two parts and determine a speed factor for each part. So if, for example, we have a flat road segment of, let's say, 700 feet, the equipment is going to travel, the truck is going to travel 700 feet. But it's going to be standing still at the beginning to be loaded, and it's going to stop at the end of these 700 feet to dump that load. In this case, we're going to divide that 700 by 2, so as if the segment length is only 350, and we're going to use that factor only once, which is, we can interpolate between these two numbers. Effect of altitude. If the equipment operates at a higher altitude where the air is less dense, the air is thinner, the engine may perform at a reduced power output. The engine power is going to be decreasing approximately 3% for each 1,000 feet above sea level. So in increments of 1,000 feet. For each increment of 1,000 feet, you lose 3% of the engine power. Turbocharged engines are more efficient at higher altitudes because they are not affected by that equation. So if you have in a problem, or if you have in real life that you're using turbocharged equipment, this does not apply. You don't have to worry about the effect of altitude. A derating factor is used to reduce the engine production based on the altitude. From this equation, the derating factor as a percentage is equal to 3 times altitude minus 3,000 divided by 1,000. 3,000 is going to be our benchmark. So working 3,000 feet above sea level is going to be where we're going to measure the equipment performance. If you are working at 4,000 feet, so in this case the altitude is 4,000 minus 3,000, that's 1,000, times 3, that's 3,000, divided by 1,000, so the derating factor is 3%. If you're working at 5,000 feet, so 5 minus 3, 5,000 minus 3,000, that's 2,000, times 3, 6,000, divided by 1,000, so the derating factor is going to be 6%, and so on. Now let's look at an example that can illustrate all of the things that we've talked about so far. Using the performance curve, determine the maximum speed of the vehicle if its gross weight is 150,000 pounds, the total resistance, which is rolling resistance plus grade resistance, both of them combined and translated into effective grade, 4%. Altitude derating factor is 0.25, 25%. Altitude derating factor is 25%. So obviously this equipment is working at a relatively high altitude. So we're going to look at this performance table here. The first thing that we can detect is 150,000 pounds. So the weight of the equipment is going to be 150,000 pounds. And we have an effective grade of 4%. So we're going to look at 150,000 and the intersection with the 4%. Here's the 150,000, the interaction with 4%. It means that for this equipment to overcome the resistance, it needs 6,000 pounds of rim pull. 6,000 pounds. But remember that at this higher altitude, we're not going to be able to use all of that 6,000 pounds. So to overcome that resistance at the higher altitude, we need actually more than 6,000. 6,000 that was not taking into consideration the effect of altitude. So we're going to derate that. So we're going to decrease that by 25%, which means dividing by 1 minus 25%, divide by 1 minus the derating factor, which is 25%. So as if we are dividing 6,000 divided by 0.75, which is 1 minus 0.25, which gives a required rim pull of 8,000 pounds. So at a rim pull of 8,000 pounds, we're going to check third gear is going to give us a speed of about 10 miles per hour. So this equipment can operate in the third gear at this altitude with a speed of 10 miles per hour. So basically, that's what we were looking for. Determine the maximum speed of the vehicle. So we determined the maximum speed is going to be 10 miles per hour. Let's look at another example. A four-wheel drive wheel tractor, four-wheel drive, which means that both axles are going to be moving. It's wheeled, it's not on tracks. It weighs 41,000 pounds and produces a maximum rim pull of 40,000 pounds. It is working at an altitude of 8,000 feet on wet earth. Wet earth means coefficient of traction is going to decrease the performance of the equipment. 8,000 feet means that we're going to have a derating factor. Operating conditions require a pull of 20,000 pounds to move the tractor and its load. Can the tractor perform under these conditions? That's the question now. We need a force or a power of 20,000 pounds. Are we going to be able to generate that power, or is that equipment not going to be able to do that? So first of all, we look at the derating factor. We have 8,000 feet minus 3,000 times 3, so 5 times 3, which gives 15%. So the percent rated power available is going to be the power that was given here, which is 40,000 pounds times 85%. Therefore, the available power is 40,000 times 0.85, which is 34,000 pounds. Now, the coefficient of traction based on wet earth, we're going to look here. Wet earth for rubber tires is going to give us a factor of 0.45. So the available power is going to be the maximum usable pull. Remember, the maximum usable pull is 0.45, which is what we got from the table, times the weight, because again we use the whole weight in this case because you have two moving axles. If it were only a two-wheel drive, we would look at the weight on the moving axle, which might be less than that. So it's equivalent to 18,450 pounds. The usable power is less than the required pull. Less than the required pull. The required pull was the 20,000 pounds. So basically, the usable pull is less than the required pull. Therefore, the tractor cannot perform under these conditions. In order to work, increase the weight or the coefficient of traction. So again, improve the soil conditions or increase the weight, because if you increase the weight times the load traction, factor of traction or coefficient of traction is going to give you something higher. So if that weight were to increase by about maybe 3,000 pounds or 4,000 pounds, when you multiply it by this, it's going to give you something more than the 20,000, which would be able to pull the load behind the equipment. To estimate the travel time, we have to account for acceleration and deceleration, and not only for the maximum speed of the vehicle. As we just mentioned a couple of minutes ago, the longer the stretch of the road, the longer the part where you're going to be moving at maximum speed, because you have to accelerate at the beginning and you have to decelerate at the end. If you're moving in a very short distance, by the time you accelerate, you have to decelerate, you haven't reached the maximum speed of the equipment. But the longer the stretch of the road, the longer part with a maximum speed you're going to be achieving. Using the average speed factor from tables converts the maximum speed to the average speed. Remember that 0.95, 0.96, etc. Let's go back here. So here, for example, if you were moving only 100 feet, you're going to be moving at only 45% of the maximum speed. So the maximum speed that we calculate from the performance tables, you're going to multiply that times 0.45. That's going to be the operating speed. Whereas if you are moving at a length of 5,000 feet, you're going to be operating at 96% of the maximum speed, which shows a big difference. The travel time is obtained by dividing the travel distance by the average speed. Travel distance by the average speed. The average speed factor applies twice if starting from rest and ending at stop. So as we said, if you're going to be moving only 100 feet, you're going to divide that by 2, and as if you're only moving 50 feet, and you apply that factor, or you apply the factor twice, because you're going to be starting from standstill and ending at a standstill as well at the end. Let's look at an example which might again explain this idea and illustrate the ideas. We are using a Caterpillar D6R standard. It weighs 39,800 pounds with a coefficient of traction of 0.6. What is the maximum speed when moving up an 8% slope? So the available pull is going to be the weight on the driving axles times the coefficient of traction. Here, by the way, we use the whole weight, which means that it's a four-wheel drive. So 39,800 times 0.6, which is equivalent to 23,880 pounds. That's the available pull. The grade resistance, we are moving at 8% slope, which is 20 times the weight in tons times 8, which is the percent. 20, that's a constant, times 20 pounds per ton, times the weight in tons, which is 20 tons, which is this one, the 39,800, almost 40,000 pounds, which is 20 tons. So 20 pounds per ton times 20 tons times 8%, the slope, which gives 3,200 pounds. That's the grade resistance, 3,800 pounds. So the net drawbar pull that we want is going to be 23,880, the available, minus 3,200, which is the resistance, which gives 20,680 pounds. That's the available drawbar pull. So we're going to go here and look at this. By the way, either is a four-wheel or it's on tracks. In this case, I believe it's on tracks because we're using drawbar pull and not trim pull. So the net drawbar pull is 20,680. We're going to go along this axis here, 20,680, which is about here, 20,680. That's going to intersect with the first gear and the second gear almost at the same point, which gives a speed of about 2 miles per hour. Now this is going to be the maximum speed. Looking at the distance it's going to be traveling and the conditions of the road, we're going to multiply that by the factor that's going to reduce that to the actual speed rather than the maximum speed. Looking at the third example here, a contractor is to use a Caterpillar D7G crawler tractor. Crawler on tracks, the whole weight is going to be used and not part of the weight. With a power shift transmission to excavate 1,500 bank cubic yards for the foundation of a large house. The swell of the excavated material is estimated to be 25%. Remember now, this problem, each word here has a meaning, so we have to break it down later on to look at the meaning of each one of these pieces of information. The tractor must push the excavated material up a 12% slope where it will be stockpiled for later removal. The contractor has measured the pile of excavated material in front of the tractor universal blade just before spillage occurs and has determined the pile length 12.6 feet, width 8.1 and height 4 feet. If you remember the equation that we used in the previous lecture, 0.375 WLH, this is something that we're going to be using here. The tractor weighs 44,400 pounds and the coefficient of traction is estimated to be 0.7. The average haul distance is estimated to be 300 feet. What is the estimated productivity of the tractor if the contractor plans to average 50 minutes of operation per hour? Lots of information. Let's break it down to see what is given and what is needed. How are we use what's given into what's needed? What kind of equations are we going to use? So we're going to break that down into steps. and look at each step. It's going to give us a certain deliverable. We're going to use that deliverable in the following steps. We're going to process it until we reach the final answer. So step number 1, the volume of material that can be moved during one operation cycle, which is 0.375 WHL. Remember that equation, but also remember that this equation gives us a volume in cubic feet, in loose cubic feet. So we need to convert that into cubic yards. Therefore, the number that we got, 153.09 cubic feet, we divide that by 27, which is equivalent to 5.67. Again, this soil, remember, is loose, so it's in loose cubic yards. We need to convert that into bank. Do we have the swell? Yes, we do. So step number 2 is to convert the volume to bank cubic yards. The volume bank is equal to volume loose divided by 1 plus the swell factor, which gives us 4.54 bank cubic yards. That's the volume of soil that's going to be moved into one cycle. Now we're going to look at the resistance. For that crawler tractor, we do not have rolling resistance. We don't have any tire flexing. Therefore, all the resistance for the crawler tractor is going to be only the grade resistance, which is going to be 20 pounds per ton per percent slope times 12% times the weight of the equipment in tons, which was given here as 44,400, which is 22.2 tons, 22,000 pounds per ton. So the total resistance is equivalent to 5,328 pounds. The usable power is going to be the maximum usable drawbar pull is the coefficient of traction, 0.7, times the weight of on the driving wheels or tracks. In case of tracks, we use the whole weight of the equipment, so 44,400, which gives a maximum usable drawbar of 31,080 pounds. The usable power that's available is greater than the required drawbar pull. Required drawbar pull is to overcome the resistance, which is the 5328. So we have much more than that. Therefore, the equipment is going to be able to move without slip. So that's the first step. Yes, this equipment can move forward. Next, we're going to look at the speed. At what speed can this equipment move? So to determine the maximum speed, the tractor will operate in first gear. We're going to look here at the available drawbar pull, which is 3,000 something, and that's going to give us in the first gear a speed of 2.1, about 2.1 miles per hour. So the maximum speed to overcome the resistance, which is 5328, not 3,000, 5328 pounds, is going to be 2.1 miles per hour. Now when returning, the tractor will return empty, going downhill. Therefore, we have no rolling resistance, and we have no grade resistance either. It's actually going to be grade assistance. So instead of using a negative number, we're just going to assume a 0, because we don't have any slopes here on this performance curve. So we're going to assume a 0 resistance. So the maximum speed available in second gear is going to be 4 miles per hour. So moving uphill, moving forward, loaded, we're going to operate at 2.1 miles per hour. Moving downhill, backward, we're going to operate at 4 miles per hour. So the tractor will return empty going downhill, no rolling resistance. Step number 6 is going to be determine the cycle time. Cycle time is going to be equal to fixed time plus haul time plus return time. Fixed time, if you remember here, it mentions something about shift transmission, power shift transmission. If you remember from the previous lecture, that was equivalent to 3 seconds, 0.05. So 0.05 minutes, that's the fixed time. The halt time is going to be the distance, which is 300 feet, divided by the speed, which is 2.1 miles per hour. Now this is in feet and this is in miles per hour. To convert that, we divide by a factor. Remember that that's going to be a constant. To convert from feet to miles per hour, we divide by 88. So 88 feet per minute per miles per hour. The return part of the cycle time, which is again a variable time, 300 feet divided by the speed, 4 miles per hour. Again, we're going to divide by the same factor, the 88, to convert from feet into miles per hour. So the total cycle time is going to be 0.05, that's 3 seconds, plus 1.62 minutes, which is the number that we get from here, plus 0.85 minutes, which is the number that we get from here. So the total cycle time is 2.52 minutes. To perform one cycle, it's 2.52 minutes. Step number 7, the productivity. In each cycle is going to take 2.52 minutes. And we have 50 minutes of operation per hour. So how many cycles in the 50 minutes? 50 divided by 2.52, almost 20 cycles per hour. Each cycle is going to be 4.54 bang cubic yards. So almost 20 times 4.54 is going to give us a total of 91.3 bang cubic yards per hour. That's going to be the total production of that piece of equipment. Another example. As you can see in the previous example, we broke it down into steps, processed the information for each step, and it led to additional elements of the problem. We combine all of these elements at the end to get the final answer. A wheel tractor is being operated on a soft roadway. Wheel tractor, so it has wheels. Soft roadway, which means we're going to have tire penetration. The tire penetration is 5 inches. The tractor weighs 5 tons. What is the total resistance and the effective grade if the tractor is going uphill, ascending a slope of 4%, or if the tractor is descending a slope of 6%? Let's look at it this way. Now we have a rolling resistance because of the tire penetration, and we have a grade resistance that's coming from that slope that we're talking about. So we need to combine these to calculate the total resistance, which is the effective grade. Total resistance as in pounds per ton, and translate that into an effective grade as a percentage. So the rolling resistance factor is going to be 40 plus, that's the constant, 40 as if you're moving on asphalt, plus 30 pounds per ton times the tire penetration. So 40 plus 30 times 5, that's 190 pounds per ton. That's the rolling resistance factor. The total rolling resistance is the total resistance factor times the weight of the equipment. The weight is 20 tons, so 190 times 20, which gives a total of 3,800 pounds. The grade resistance going uphill is equivalent to 0.04, that's the slope, times 20, which is 20 pounds per ton, per 1% of slope, times, to convert that into times 2,000 pounds per ton. 20 tons, that's the weight of equipment, 2,000 pounds per ton for the to convert the total into pounds. So the total resistance is equivalent to 1,600 pounds. Descending is going to be negative. Remember that going uphill is positive, downhill is negative. So the resistance going downhill is negative 2,400 pounds. So the total resistance, if you're moving uphill, is rolling resistance plus grade resistance, 3,800 plus 1,600. That's the total of 5,400 pounds. Going in the opposite direction, descending downhill, is going to be the same, 3,800 minus, in this case, 2,400, which gives only 1,400 pounds. Now to convert this resistance into effective grade, we're going to divide by the weight of the equipment and 20 pounds per ton for each percent of slope. So 5,400 divided by 20 times 20, that gives an effective grade of 13.5% uphill. So converting the rolling resistance into a grade resistance is almost 9.5%, which is the difference between 13.5 and 4. And for the downhill trip, it's going to be that 1,400 divided by 20 by 20. So it reduced the total resistance is going to be 3.5%. Remember, we had negative 3.5, so it's exactly the same 9.5. If you notice here, 9.5 is the rolling resistance. When added to the 4%, gave a total of 13.5. When you subtract the 6, it gives 3.5. So 9.5 plus 4, 13.5. 9.5 minus 6, that's the 3.5 when descending. This is basically an introduction about how to calculate the slopes, how to calculate the resistances, how to calculate the speeds, and how to calculate the cycle time. We have posted online a more comprehensive example that shows different segments of the road, uphill, downhill, and it follows the same procedure to calculate the different segments into different steps, and then we combine that at the end to get the total cycle time and therefore the total production of that equipment. I'll see you in the next lecture.